a look at this question. Now, as usual, I'll try and give you a key to answering this question. My key to answering this question is to understand that the gap between the energy levels in an atom gets smaller and smaller as you move further from the nucleus. So the IB like to use this word convergence. Now, we have a couple of different ways of representing the energy levels around an atom. This is the classic model here that you would know from maybe junior science, and this is Bohr's model after Niels Bohr. So that's Bohr's model of the atom. Now, Bohr's model is effectively the classic concept of central nucleus, which would be like having the sun at the center of our solar system, and then the planets orbiting around that central sun. Now, we have these different energy levels, and they can be represented as the circles around the atom's nucleus. Those energy levels, the evidence for those energy levels came from what we know as emission spectra. So in an emission spectrum, electrons gain energy from certain frequencies of light, and as those electrons gain in energy, they jump to a higher excited energy state. Now, I was going to just look up an image and put it onto the page, but you do need to know how to draw the emission spectrum for hydrogen, so I'm going to do that for you now. It doesn't have to be perfect, but you do need to get the key points across. So we're going to start with energy level 1, or n equals 1. Now, the key thing here is that we're going to have a big jump from n equals 1 to n equals 2. But then I'm just going to get rid of that word emission for a second. As we jump from energy level 2 to energy level 3, you should notice that the gap starts to get smaller, not greater. So there was a big gap between n equals 1 and n equals 2, but then the gap starts to get smaller. And this is what we mean by convergence of the energy levels. It's getting smaller again. And if you were to continue, you would eventually reach a point where the energy levels converge so much upon each other that they're effectively at their maximum. And if you go beyond that point, then you have removed the electron from the atom, in which case you have achieved an ion. So that's the process of ionization, is where you go beyond the top energy level in an atom. Now, hydrogen is the only element you need to know the emission spectrum for. And that's good because it's the simplest element to deal with. We're only talking about one electron. And in this question here, they're asking you which transition will give you radiation with the longest wavelength. So this is emission that we're talking about here as opposed to absorption spectrum. So just to be aware, if you start off with an electron down here at energy level equals 1, and then we're going to excite it with a certain frequency of light or radiation, then that electron will take that energy and it will jump to a next energy level. Now, it could be directly to n equals 2, or it could skip n equals 2 if it has enough energy and go all the way to n equals 3. But in any case, the electron has absorbed energy, and that's what's known as an absorption spectrum. Now, the absorption will end up exciting the electron to a higher energy level or an excited state, and then that electron can't stay there forever. It's going to lose that energy and go back down to its original resting or starting point, the ground state. So when this electron drops back down, whether it's from n equals 3 down to n equals 2, or from n equals 3 down to n equals 1, as that electron drops back down to its starting point, it's going to emit radiation of a certain frequency. And that's what we're talking about when we talk about emission spectra. What we have in this picture here, just above the Bohr's model with the circles, is we have the emission spectrum for hydrogen. And we have some key colors that pop up in the hydrogen emission spectrum. We have red light with a wavelength of 656 nanometers, I should say. Then you have this kind of a turquoisey color at 486 nanometers, a purple color at 434, and this kind of pinky lavender color at 410 nanometers. Now, that is unique to hydrogen. So emission spectra are sometimes referred to as elemental fingerprints. So it's like an elemental fingerprint in that no two fingerprints or no two elements will give you the exact same emission spectrum. So this is a great way of identifying what elements compose the stars or planets that are far, far away from us, light years away from us, but you can look at what light is being emitted from those planets and therefore figure out what elements are present based on the emission spectra that you see. And this is actually the way helium was first discovered, which is a fact that a lot of people wouldn't know. So helium was actually discovered in this way. So check it out, do a bit of reading on how helium was discovered through its emission spectrum. Back to this question, you have a choice of a couple of different transitions here. Now there's one option in this question which you can discount straight away, and it's the answer B, because B is talking about an absorption. And for answer B, they're talking about jumping from n equals 1 up to n equals 2. So that would be absorption of energy, and therefore that's why we can straight away discount answer B. Now the other answers are all emissions. You can see that you're going from a higher energy level down to a lower energy level in all the other cases. And so we need to just figure out which one is going to release. We just need to figure out which one is going to release the least amount of energy, because this question is asking us to figure out which transition will give radiation with the longest wavelength. So you do need to remember from junior physics the relationship between wavelength and energy. So wavelength is inversely proportional to energy. In other words, if you have a low energy change or emission, so if you have frequency radiation with a low frequency or low energy, then you will have a long wavelength. You probably want to just review the electromagnetic spectrum concept, so radio waves, microwaves, all the way up to X-rays and gamma rays. But radio waves have a very long wavelength and a low energy, and that's why you can play a radio in a room and not be worried about radiation damage from radio waves. Whereas if you have exposure to X-rays for long periods of time because of their short wavelength and high energy, you're going to get damage from that X-ray exposure. So in this case, we're looking for the transition which will emit the radiation of the lowest energy or longest wavelength. Now, I've just been thinking about the best way to conceptualize this for you guys. So I'm going to use a little stair concept. Okay, so I've just drawn in my little stairs now beside our original hydrogen emission spectrum diagram. And hopefully the stairs will help illustrate now how, as you move further from the lower energy levels, the upper energy levels start to get progressively closer together, or they start to converge. And this means then that a transition from energy level 3 to energy level 2, for example, is not going to have a great difference or drop in energy. So if I just highlight that for you, one of the options in this question was to drop from energy level 2, so we have a little electron here, and it's dropping down from 3, I should say, down to energy level 2. So that's not a great difference in energy. Similarly, from energy level 4 down to energy level 3 would be even smaller again, but that's not in one of the options for the questions. So the other options you have to look at would be from energy level 2 down to 1. Now you can see that's a bigger drop in energy. The reason the electron is so low in energy when it's beside the nucleus is because that positive charge of the nucleus, or the effective nuclear charge, is far stronger the closer you are to the nucleus. And the last option you have to look at there is option C, which of course is a big jump. This is the largest jump possible from energy level 4 all the way down to energy level 1. So as we said, we're looking for the lowest energy change because this will give us the longest wavelength of radiation emitted. And so the lowest energy change here, hopefully it's easy to see now with this stairway concept, will be from energy level 3 down to energy level 2. And so from energy level 3 down to energy level 2 is answer D.